stuff. All right, here we go. So this graph over here, this is the population distribution. Population. This graph over here is one of the many samples from the right. One of many samples. To the, sorry, I don't know my left and right, to the left. And this graph right here is a sampling distribution. What's a sampling distribution? This is one of the tricky parts. It is not a population distribution. Notice it doesn't look anything like that graph up there. It's not the graph of a single sample. The samples all look pretty similar over there. They look like mini versions of the population. Okay? There's a whole bunch of people crowded over here, and there's a few people straggling out there in the high end. A sampling distribution in this case, I'm focusing on the mean, is a distribution of many sample means. So in this case, I have means from 1,001 different samples. 1,001 different samples. Each of size 100. What I want to do is take a look at the spread here. So to look at the spread, I got to go back to stat key. Actually, the standard error is good enough. Let's write that on another one. So I have a standard error up there of 0.588. So new page. So this is baseball salaries. Make salary as 1L. And what I want to do is I want to look at the sample size N versus the standard error. And I have a sample size of 100, and my standard error is 0.588-ish. Okay. I'm going to do it again, make sure I get a number similar to that. So I'm going to reset the plot. I'm going to keep it at size 100, and I'm going to just generate another 1,000. This time the standard error is 0.593. It's in the ballpark of 2 decimal places. I do it again, generate 1,000 of them, 0.575, in the ballpark. Okay, so I'm going to stick with what I had a minute ago. I'm going to change the sample size. What if I make the sample size 200? Bigger sample size. And I generate another 1,000 samples. Notice the standard error this time is 0.383. So you note that. So I let n equal 200, and I got a standard error of 0.383. And I'm just going to do a couple more to see if they're in the ballpark of that. So reset, keep it the size at 200, do 1,000 samples, 0.404, a little higher, reset 1,000, 0.394, reset another 1,000, 0.399. Okay, so the 383 is a little low, so maybe I'll up that one based on the other ones and say maybe it's more like 0.390-ish. Okay, let's do a couple more. Let's go with a sample size of 400 for fun. So change the sample size to 400. Generate 1,000. Now, usually I do more than 1,000. I'll do like 5,000, but I just want to get this done quick. 235. Reset, try again. 235. Reset, try again. 236. All right. Higher the sample, the standard error is kind of stabilizing a little bit. 400, 235-ish? Get that right?
236.
Yeah, I'm just gonna, and I saw the 235 a couple of times, so I'm just gonna go with that one. So here's what I want you to do. I want you to make a prediction. So first I went 100, I got 0.58-ish. Then I went 200 sample size, I got 0.39-ish. I went 400 and I got 0.235. What if I dropped the sample size way down? Like what if I did something like with a sample size of 50? what do you think is going to happen to the standard error? It's going to get bigger or smaller? It's going to go up, it's going to get bigger. Some people online are saying, yeah, so it seems like the bigger the sample size, the smaller the standard error. So if I go the other way, the smaller the sample size, the bigger the standard error. Let's ask STAT243 what happens when we try to make that kind of analysis. So we're going to drop the sample size down to 50. And then we're going to do 1,000 samples of size 50 from that population. And here we're getting a standard error of 0.86. Now, I think because the sample size is small, there's going to be a little more variability in what the standard error will be based on the previous examples. So 0.862, 0.834, 0.9. Yeah, this is jumping around a little bit more. Okay, so that's why it's kind of in our best interest to get as big a sample as we can afford to get, right? But then you got to get the sample. That can be expensive. So let's call it 0.892 for fun. So what we're seeing here is that the sample size is inversely proportional to the standard error. And my statement isn't quite accurate because I don't know that it's a true proportion. So I guess I should scale that back a bit and say related. It's inversely related. Oops. Related, there we go. And what I mean by that is as the sample size increases, the standard error decreases. There's a section in the book on this. Make sure you read that section in the book. It is an important idea. And this relationship about how they're related to, we'll get to that later. It turns out there is a formula for it, but it's not a straight proportion. Tiny bit more complicated, but not too bad. All right, let's look at a new example. Then we're almost out of time.